ultimate visualization display.
Well, thank you very much, Xavier. Had a lot of fun today meeting some of you and talking with you and learning about the culinary, I guess the culinary arts. It's not culinary arts. It's hotel management. We had some interesting experiences there today. I would like to talk about the ultimate visualization display. And in doing so, I want to go through about 400 years of computer display technology. So, as you might imagine, some of that's in the future, but I think it's actually kind of interesting. But first, I want to go into the past, and I want to read you a quote that Ivan Sutherland made back in 1965, where he said, "The ultimate display would, of course, be a room within which the computer can control the existence of matter. A chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would be fatal." So that would be quite the display. I don't think we're going to quite get to that right away, but I think the characteristics that this calls out are that the room needs to be, the display needs to be indistinguishable from our senses perspective from reality. So, and what he described included touch in particular. In fact, most of what he described was touch. In our visual display, we can't sit on the chairs we make pictures of, and we're not damaged by the bullets we make pictures of. So I think that sense of touch is one that's very hard to do right now. So I'm going to talk about more the visual aspects of that. But let me start with some fictional examples. I'm going to go way into the future, or maybe the past, depending on how old you are. This is a picture of the Holodeck, which is a device on Star Trek ships and in some stations, apparently, I learned from Wikipedia, that was able to put you in a virtual world that was different from where the display was. So the empty holodeck is up in the top left, but as you walk in to that room, you might see something like this, which is just a hill on some planet with grass on it. And you walk in and it's exactly like reality. If you find a horse in there and you can sit on it, it'll run off with you and carry you away. So it is the ultimate reality, the ultimate display. But it's also fictional, and it actually was designed in 2350, I think. So we've got a little time to wait for that one, so some 300 years in the future. A little bit less far into the future is another kind of ultimate display, which I think for its viewers was much the same as the holodeck, at least kind of in how they sensed it. But I don't know. It was a little different in how they sort of were involved with it directly. I don't know if you can, this is from The Matrix. For those of you who haven't seen it, The Matrix plugged people into this kind of, I don't know, this network, this matrix of wires. You can see arms in here with wires going in, and this is a baby being grown in the matrix, and it has lots of little wires coming out of it too. And those wires were how the display showed things to the quote-unquote viewer. So maybe not such a nice thing as the holodeck, but I suspect very effective. And how many of you have seen The Matrix? Okay, so you know that it was a very effective display until you got really good at figuring out what was there and what was not there. Anybody know when it took place? 2200. I'm not going to give you a chance to go to Wikipedia and find the answer. So 2200, only 180 years in the future, 190 years in the future. So we're moving back towards today. So moving yet further back, this is a snip from the movie Minority Report. And this is another kind of a display. It's nowhere near as tactile, no touch here, but we do get a sense of interacting with a fancy thing and directly manipulating pictures and being able to see through this device that really doesn't get in the way too much. And that's kind of the point I wanted to get in here, that one of the aspects of the ultimate visualization display, I think, should be that it doesn't get in the way too much. So this is something where the display is well, it literally is transparent. It also, you can see through it. I think that was more of a cinematographic, it's a hard word to say, kind of issue, because that way they could shoot pictures of him while he was working the thing. But it's also transparent in that you're manipulating these images and not really thinking about it too much. At least it looks that way. From stories I have heard, in fact, he had to take regular breaks because his arms got completely worn out from having to hold his hands up in the air way too much. So it was maybe not a perfect interface, but it looked really cool. So, and again, smooth and seamless interaction is the thing I wanted to call out here. And in a similar event, I'd like to characterize that smooth and seamless interaction with one last fictional display. Now, I don't know when this was set because it's in sort of a parallel time universe, but let's say it's in the future. This is the Wizard of Oz, and you can see the ultimate display up here. And one of the things that I think is really important in a display is seamlessness and a lack of things that distract you. And I don't know what the right word for that is. I can think of good words for almost all the other characteristics of the ultimate display, but that one I can't. So I'm going to call it no curtain. And that comes from the curtain here. I think that in addition to not being able to see the wizard behind the curtain, you shouldn't see the curtain at all. The whole thing should be as transparent and as kind of not there as possible. Okay, so let me go into some historical nonfiction displays now, and I'm going to draw mostly from Brown here in work that was done in the past. I will start describing the first display that I used at Brown, which is the Ramtech monitor on the left there, which was driven by the hardware down on the bottom of the picture. We made pictures on 16mm movie film by shooting pictures one frame at a time off of this frame buffer here, using this Bolex camera. Actually, it wasn't exactly this camera. I looked these images up on the web. But we used a Bolex camera very much like that, and we would send them off to Boston every day in the morning. We'd get up and get the pictures that were shot overnight on the camera sitting in front of the monitor in the dark, because we couldn't do it in the daytime because it was too light. We'd send them off on the bus to Boston. That afternoon, they'd come back. We'd look at them on the projector. Ultimately, we'd edit them together with this cool little device that uses tape to hold the frames together. It was a very different experience from editing movies today. But it produced pretty kind of interesting results. And I'll show you one that we made in the early 80s. This is a movie that we called the Hypersphere. Again, we did this one frame at a time. And it shows how a three-sphere, which is something you can't have in our world, you need 4 dimensions to kind of hold it. It shows how that can be cut up into circles. So what you can do in our dimensions is hold a projection of a 3-sphere that fills all of our space. And that's basically the same as a projection of a 2-sphere that fills all of a 2D plane. So you need 3 dimensions to hold a 2-sphere. And I'm not talking slow enough, but we'll get one of those in just a minute. Then you can project it so that all the points on the sphere map to one point on the plane. So here we go. Here's our plane. Here's our sphere. The 2 poles at the sides now are mapped to those 2 spots. And we can slice up that 2-sphere into circles. It starts at a dot, circles that grow, they shrink back down to another dot, and that defines an entire projection of that whole sphere, which you can now see colored, projected down into the plane. So if we rotate the sphere, that projection rotates as well. So this is not earth-shattering math yet, but when we go to the next dimension and try and look at what happens with this 3-sphere, which is much bigger, we can do the same thing. We start now, instead of with a point, we start with a circle, and we have another circle which is linked with it, and then there is a family of toruses that grow up around one and back down around the other. And that's the analog of what's happening with the circles going from one pole to another in the 2-sphere. So remember, we're looking at a projection into 3 space of this slicing from 4 space. When we rotate that projection around, rotate the 3D sphere, the 3-sphere around, we get different pictures here. And we can do the same thing by rotating in various directions to try and get a sense of what's happening in that 3-manifold without boundary. It was interesting today. This is the first place I visited in any recent time where we talked about manifolds and foliations of them. This is a very famous foliation of the 3-sphere called the Hop foliation, which is actually, if you look at the curves that bound those little stripes in that flat section, that flat torus that kind of goes through infinity, they're all circles too. So every single one of these tori can be made up of circles, as can the initial torus and the torus on either end that are linked. So what you get is not just a family of tori that fill this 3-sphere, but a family of circles that fills this 3-sphere. There's also some interesting connections back to linear systems, linear Hamiltonian systems, coupled pendulums and stuff like that. And now, I'm sure everybody is completely confused with what this has to do with the ultimate display. So the reason I put this in here is because, 30 years ago, 25 years ago, this was a pretty darn good display. It had a bunch of properties that made it really useful. So people can look at that movie and listen to me talk about it. They can look at it a bunch of times and see something different every time. So it provided a kind of a service, if you will, a way to understand what was going on in this complex domain in a way that I think you can't really get by reading a book or looking at still images or even by writing down equations unless you're really good at understanding equations. The things that it provided that were the most use, I think, were that it had enough resolution spatially that you could interpret it as a picture of something. So it kind of matched our perception well enough that we turned it into a picture. So if we had 4 pixels up there, 4 big blocks, we would not see a torus. But this matches our perception well enough to be able to see a torus. It also matches our brightness perceptual abilities. So there was lighting and shading on there, there were colors, and all of that requires a certain amount of depth of color that I think you need to be able to do to have a good visualization device. And the third piece of our perception that it matched was our ability to see motion. So film is shot at 24 frames a second. People don't see motion well at 24 frames a second. It turns out they need about 50 frames a second, or actually 48 is enough. So every time you look at a film, you see every picture flashed twice. So it's not actually a different picture all 48 times. Every other time it's the same picture as the one before. But that flicker thing, it's called the flicker fusion frequency, I think, is what matches our perceptual abilities and tricks our brain into seeing things as moving. So that's the third piece of perceptual matching that kind of display did that I think made it a really good display for the time. There was really no other way to do this kind of stuff back then. And so, of course, today, I think my son, who's in high school, could probably implement this in JavaScript in about an hour and a half. So the world has changed. But at the time, it was a very good, not interactive, but effective way for people to look through stuff and try and understand things that were complicated. I should also mention that one of the reasons that I think it was a good display is that film had been around, way before computers. There have been 50 years of development of the technology that let you put down the right amount of silver at every point to make things the right amount of transparency and the understanding of the flicker fusion frequency and all the things that go into making film work. So my last example of a historical display is also from the early 80s. This is a mock-up of a Sonar repair manual that Andy Van Dam built that kind of predates the idea of tablets, but is in fact a design for a tablet device. They made a bunch of these prototypes and also a bunch of software that ran on that Ramtech display that tried to have that kind of non-invasive, no curtain effect way back in the 80s. Okay, so what makes visual reality? So I talked about how film captures a bunch of different properties of our perceptual system. And it turns out that you can measure how much of each of these things you need to kind of trick our perceptual system into, or to get to the limits of our perceptual system. So it turns out our eyes, how many of you have an iPhone 4? So the display on an iPhone 4 is called a Retina display. And that's because it has 300 dots per inch, and 18 inches away from my eyes, each one of those dots, those pairs of dots, are separated by the same distance as the receptors in my retina. Retina display. So the way to measure that is the angle between features that you're seeing. And it turns out our eyes have about 1 arc minute of spatial resolution. If you can put pixels up that close together, then you get something that you can't really see the pixels individually anymore. So this is a Retina display, but so would be this if I were standing far enough away from it. So it's not a function of pixels per inch, it's a function of that angle that it makes with the eyes. So now, I don't know about you guys, but I have 2 eyes, and most computer displays ignore that fact. Now, not everybody can see stereo, but most people can, and it turns out stereo really helps you to see certain things, like 3D. We don't use it for everything we look at. Our stereo works out about to a meter or so it works out kind of as far as we can reach with our fingers. Not much further than that. We get lots of other cues for distance, but I think the ultimate visualization display needs to match that 2-eyed vision, not just monocular vision that we have. So the frequency at which things need to change in order to get that motion that I talked about in film, because of the brightness of projector bulbs, is about 48 frames a second. Or I should say 48 flashes a second, 24 frames a second. With modern projectors and monitors, I'm going to bump that up to 60 because I think that is probably safe. If you have something that's bright enough and that's moving fast enough, you can mess it up. I'm sure you've seen TVs that have refresh rates of 240 hertz, which is fast enough to do just about anything. We're not going to see beyond that. But for most things, 60 frames a second is enough. So when it comes to brightness contrast, if you look at a grayscale image, people can distinguish some couple of 100, 300, 400 maybe different levels of gray. So I listed that as 2 to 3 orders of magnitude in terms of brightness contrast. Now, a lot of times people say, well, but wait a minute, we can see things in 1 candle, dark rooms, candlelit dinner kind of thing, and we can go out in bright sun on a beach. And isn't that 10 orders of magnitude? And yeah, the answer is yes, but we really can't see all of those at the same time. When we look at stuff in a dark room after being at the beach, it takes us a while before we can actually see anything, and vice versa. When we go out of a movie theater, it takes a while before we can see things outside. So there's an accommodation effect that gives us a huge dynamic range of vision, but at any given level of that dynamic range, we really can only make out details of about 2 to 3 orders of magnitude. So another thing that's important in our visual system is in order to see color, we have to have a certain amount of brightness. When you're outside at night, in the dark, or inside at night, when you're anywhere in the dark, and you look at things, they're not colored anymore, or they're much less colored than they are in the light. If we turned out all the lights in here, it would look much less colorful. So it turns out that you need enough absolute brightness in your imagery to be able to see color. And I'll give you an example of where that didn't happen in the past. And then finally, there's still this one other funny characteristic that I don't quite know how to describe that is going to kind of capture all the other pieces of the ideal visualization display, and that's the no curtain piece. So that's the thing that keeps us from being distracted, the thing that has the interfaces that are smooth and easy to use and don't get in our way, and the lack of funny artifacts. So one of the things that happens sometimes in a computer display with stereo is you'll feel like there's some ball that's right in front of you, and you put your hand behind the ball, but the ball doesn't cover your hand up anymore because it's really being displayed behind your hand on the screen. So that's an example of a curtain issue. There are lots of funny visual cues we use that can get messed up in various kinds of virtual displays. Okay, at this point, I'd like to take a little pause for any questions you might have about any of this perceptual stuff or the examples that I've given. By the way, I'm happy to get questions anytime. It's always easier to know where people are not getting stuff. Or I could just keep going. When I first started teaching, someone told me that when you ask a question, you have to learn to count to like 30 before you give up on people coming up with one. But I never was very good at that. So let me talk about a cave that was built at Brown right before I got there in 1998. So I'm jumping from, I discovered last night that my examples, the film example was 26 years ago, and this example is 13 years ago. And I don't know, there's a weird 13 periodicity here that I kind of was a little bit freaky. So this is an example or a model of the cave that was built at Brown right before I got there. If any of you know Andy Van Dam, he's the model in there. He always wears a sweater over his shoulders with the arms in front, so that's how you can tell it's him. This particular cave is a virtual reality display device. So it's kind of an ultimate visualization display, or it was the best we could do in 1998. So it's got 3 walls. How many of you guys have been in a cave, seen a cave demo? So they're pretty cool. This particular one has 3 walls, about 8 foot square each, and then an 8 foot square floor. And all of those are projection screens. The floor is projected from above. All 3 walls are projected from the back. You wear funky glasses, and he doesn't have his on. But they show you one picture in each eye at a time, so you can see stereo imagery. So you see real 3D stereo, and as you move your head around, this is one of the coolest things about these cave devices, as you move your head around, objects in front of you get redrawn so that they hold still in space. If you've ever looked at a stereo picture, usually you move your head around and the thing kind of rotates or deforms to follow your head. You can't look around the back of it because it's just one picture. But in the cave, you can actually walk all the way around the back of things and see the other side. So this particular cave had about 4 to 5 arc-minute pixels. So what that means is that each, let's see if I can get this right, each pixel could be seen with a 4x4 or 5x5 array of receptors in our eye. So much bigger, much less resolution than you would want. This is the best you could do in 1998. There was about 1,000 pixels on each edge of that display. So this thing was cool. So for those of you who've been in a cave, anybody think it wasn't cool? That's a good answers. There were a lot of you who actually been in a cave. I'm kind of surprised. Was there one here? Yeah? Good. And is it still here? Is it still running?
I took it over. I'm not sure they're running it.
Okay. Nobody showed it to me today, so I wanted to see it. So, and do you know when it was? Do you know what the resolution on it is?
1280, I think, per screen.
Per screen, and the same sort of 8 foot kind of screens? Yeah, so roughly the same. So it's probably about the same vintage then. Yeah. So I like to think of there being something really magic about this thing. You go in there and I don't know, you kind of get lost in it. It really builds this picture in your head that is really different from what you can see in a regular 2D display. So we played with it for a bunch of years and built some applications. I think that there are a couple of real potential wins for something like this. One is the ability to kind of work in the large. So being able to move around and move your head around and see different things and even walk and interact with your body is something that's very hard to do, say, with a laptop. So it really gives you an ability to be able to get at that kind of functionality. And of course, you have way more visual coverage, so your whole visual field is filled, and I'll come back to that in a little bit. You also get not just the sort of peripheral vision of the display, but you can turn your head and get full vision, full resolution vision in all directions. And one of the things that we do as humans in thinking and in solving problems is we don't actually keep a model of the whole world in our head. We keep refreshing it by looking at things to see, oh yeah, there's chairs over there. I didn't remember there were chairs over there. I had to look back over there. Even though they were still in my peripheral vision, I'm not sure I would be able to say those things that over there that I see little gray blobs of were chairs unless I looked over to refresh. So that's a constant operation that we unconsciously do to help us in thinking. So some of the things that I did while with this cave was to build a bunch of scientific applications. And this slide illustrates a couple of those, or a few of those. In the upper left, there's an archaeological analysis application that we built for looking at artifacts from the great temple site in Petra, Jordan. I'll go into a little bit more detail about that later. Going around clockwise, there is a bioengineering guy standing inside an 8-foot tall model of a coronary artery, watching blood flow kind of stream past him and trying to understand where plaques form on the sides of the arteries. Just down to the right, on the far right, is a bat flying with little particles swirling around it in the airflow. Bats are fascinating little, well, some of them aren't so little. They're fascinating animals that there's 1,000 species of them that range from insect size to 6-foot wingspans, and they have the maneuverability of their wings that we have in our hands. So the bones in their wings are actually analogous to our finger bones. So they're really different in their flight than birds are. We built an application called cave painting that lets you author things in this virtual reality environment. And we did a bunch of stuff with brain imagery, like you see in the two images in the left bottom there. So from these applications, we learned some things that worked, and we learned some things that didn't work. We compared the cave display to desktop displays like this little fish tank guy down here, and I'll talk about that a little bit more. We had artists use it. One of the great things about the location of Brown is we're right next to the Rhode Island School of Design, so we get to work with artists and designers, and I have them as collaborators on many of my research projects and some of my funding. So, but before I go into details about that, let me set a little bit more of the stage in 1999 with a paper that was written by Fred Brooks right about the time that we got our cave. This is a paper called "What's Real About Virtual Reality?" So in this paper he said that virtual reality was barely working, and he considered that a very strong positive statement. So that was in contrast with his statement 5 years before, which was that virtual reality was not working. So barely working was a big step, and I think that's a fair statement. It was to the point where you really could see 3D, you could get immersed in these environments, but it was still early on. Now he came up with a bunch of observations about where it was working, and one of those was entertainment, which seems pretty clear, but he kind of discounted that, and I will as well. In some ways, we're willing to suspend our disbelief for entertainment, and I think that's not so true for scientific endeavors. But he also pointed out that there are training applications like airplane pilots and ship pilots. There are astronauts getting trained in caves, or there were then, or getting trained in virtual reality environments. They were getting used at the time for car design reviews and ship design reviews and tractors and buildings by architects. There were some psychiatric treatments happening at the time. The one he mentioned was fear of flying. So I think there are some other examples of that now, but that's something that virtual reality was able to do then as well. And some interaction with scientific data, although that was kind of just getting started at the time. So I just want to mention that as something that kind of predated the observations that that we made and we were building on top of. So I want to go through a set of things that we learned about the cave that pertains to a ultimate visualization display. So the first one is you can make a good demo with a cave. So those of you who have seen one know that that's true. But there really is some magic there. And I think there's some questions there about where that magic comes from, which I'd like to be able to answer, and I haven't been able to yet. Anybody know why? Why is it magic? Oh, well, I can't figure it out either. So the second lesson that we learned is that making cave applications takes a lot of time. So we could meet with some application person, some scientist in another discipline for a couple of hours and learn something about what they wanted to do. And then we could spend 2 weeks with some designers from RISD or from our group and sketch out an application. And 2 years later, we could have it implemented. So it's just like anything with code. It seems to take forever to iterate through the designs that will actually make things be usable and nice. And part of that is, I think, Fred Brooks's observation that there is no silver bullet. And by that he meant there's no way to speed up the sort of production of software in terms of the real complexity. It's complex stuff. Although he did say that there are ways to get rid of some of the, what he called accidental complexity. And I think that there's room for that in developing these kind of applications, but there's also real complexity there that may be hard to get rid of. So let me go into that archaeology application a little bit more as a lead into the third finding that we came up with. So this is the cave room. There's a temple map down on the bottom, and on top of that we can pull up a model that's sort of a scale model of the ruins of the temple as they were excavated there. We can also go into a full-scale model. Now this is one that you fly around. So this is one that's big enough that it's actually the same scale as the real world. So you can get down into the areas along the side of the seating there, or walk up to the stage area, and it actually kind of towers over you. And this is much like what the folks that were there digging would see when they were digging. And so it kind of gave them a familiar environment with which to pull up the GIS stored data of all the artifacts, the hundreds of thousands of artifacts that had been excavated and recorded as they were dug out. So one of the things about architecture or archaeology that's kind of unfortunate is that when you're done, it's destroyed. So you gotta work from the record afterwards. And this gives a way to work from the record while still having that 3D context in which the record was created. And we did find that folks were able to use that 3D context to be able to do better analysis of their archaeological data. So I characterize that as the spatial relationships that the cave can provide you with is part of the magic and provides something that's valuable. I think it also helps if that spatial relationship is one that you're already familiar with. So for the folks who had actually been, excavating there in Petra, they were like, wow, this is just, it's like being back there. And that was kind of cool. But even the ones who hadn't been there, developed an understanding of that space.
I couldn't tell from the slide, but it wasn't supposed to be photorealistic.
Not photorealistic at all. Nope. You could have, but we didn't.
You chose not to, but that wasn't important for this application.
Right. So the idea was to give them the geometry, the space. Yeah. So it might have been wise to put some textures on to give more of I know flat walls are very hard to judge the shape of. So some texture, like we had that stone texture on the wall of that room. I think that helped people to judge the shape of that, and it might have helped on those other walls too. But we were also running up against, rendering limitations at the time, so we left it flat. One thing we did find is that they didn't want a fancy textured reconstruction of what the temple might have looked like when it was in use. They wanted the ruins, because the ruins were what was there when they dug it up and what's there now, what they can go stand in. And that seemed to give them a better, more familiar environment to do their analysis in. So I thought that was kind of interesting, that the familiarity of the ruins was more valuable to them. So we had a couple of, so I'm always in search of this magic, and I had another hypothesis about it. So the hypothesis was related to your question about texture. So we noticed in that wall where we put the map on the floor that the texture kind of really gave you a sense of presence in the room. And in fact, in another application, which this shows a video of, we had a brick wall up that was exactly coincident with the walls of the cave. And one of the grad students came in and said, wow, this brick wall is like the most compelling stereo I've ever seen. And so of course we said, well, that must be important. And we did an experiment, and I'll describe that experiment to you. We called it the Great Potato Race. You'll see why in a second. So we picked a bunch of contexts. We sort of felt that context must matter in the cave. And so we thought, well, maybe not just being magic, maybe it actually helps you do something. So we picked a task for people to do. We had them work in these 4 different contexts. So the upper right one is the brick context that I showed you before. And then the other ones are sort of the other possibilities. The hypothesis was that having the cues about where the world was nearby would help you kind of analyze things and keep your body frame of reference more solidly anchored. So you can imagine that standing in the middle of a blank, dark plane, you might get vertigo trying to look at things because there's nothing behind them to kind of anchor you to. So these were the 4 contexts we had people work in. The task we chose was to take a potato-shaped object, this is where the potato race comes from, and determine whether there's a square protrusion on it or a triangular protrusion on it. Okay, you say, not a very hard task. So we had to make it harder because otherwise everybody would get it perfect. And we did that by adding noise to that potato shape. So you can see that it gets a little harder when you get over there. So in fact, on the right, it's almost impossible to do in a still image. But when you have stereo and you have the ability to use motion parallax and stuff like that, turns out you can still do this about 75% of the time, which is just what you want for a user study like this. You want it to be about the level of halfway between guessing, which would be 50%, and getting it right every time, which would be 100%. That's kind of the sweet spot. So we had folks interact with these potatoes in 2 ways. One was to hold a device that kind of skewered the potato and turn it around and be able to look at the potato while we were doing that. And the other was that the potato just held still, and we used the body kind of rotations, the body manipulations of the world to walk around the potato and try and figure out what was protruding from it. Now you remember our cave was missing a back wall, so we had to be careful not to put the protrusion where you could never see it. So sadly, context didn't matter. I hate coming up with negative results. It's so annoying. But what we did find is, in addition to looking at this in the cave, we looked at it in a fish tank display, and we found out that, in fact, not only did the context not help or hinder, at least in the measurements we could do here, the cave was slower and it was less accurate. Bummer. So not a good advertisement for caves, but still, I think, an interesting result. So right, and I will summarize that here with the virtual context didn't help. So I actually think that there are contexts where the virtual environment will help. I think that the archaeology example is a place where the virtual context did help, but it was a different kind of task somehow. So we kind of have to figure out which tasks is it going to help for and which tasks is it not going to help for. So for my next couple of, my last two findings I want to go over, I'm going to go through 3 different scientific applications. So in one of them, we had doctors look at, or brain scientists anyway, they weren't all doctors, look at complicated anatomical models like this, and we had them do it in the cave. This is that same video I showed before, but instead of the bricks this time, you should look at the model in the front, which is the anatomical brain data set. And we had folks come in and look at this in this context and in a fish tank virtual reality context. Now, I talked about the fish tank a little bit before, but let me give you a little bit more detail on that. So a fish tank setup is a regular monitor, and it has stereo display on it, just like the cave walls. It also has head-tracked stereo, so that as you look at the monitor and you move your head around, the stuff inside it holds still. And what that lets you do is that same kind of head motion and controlling what you're able to see with your body that you can do in the cave, but at a much smaller scale. It's kind of like looking into a little aquarium behind the screen of the monitor. So once again, desktop performance was better than the cave. And another thing we found is that the 4 out of 5 doctors surveyed said we'd rather use the desktop. And they actually said why. They said it's much crisper and brighter. So that was one thing that they were worried about. And they also said we can sit down. So that was kind of interesting. I hadn't really thought about the kind of the comfort level, but that's the Minority Report thing too. That some of these interfaces look cool, but they're not necessarily efficient. Yeah.
I would not be surprised. This is what we call an outside looking in scenario, which is where the map caves overkill, whereas in Petra, it'd be inside looking out.
That's right. The same thing is true for the potato thing, right? Yeah. That was another outside looking in kind of task. What's that?
You didn't need the world.
That's right. So now, the brain folks weren't restricted to staying outside looking in. They chose to. They could actually get right in the brain if they wanted to and look at it. But they didn't do that, and we didn't know for sure that that's what they were going to. We didn't know for sure how they were going to interact with it. They mostly kept it at about human scale and just, as you said, looked in from the outside. But I agree that a lot of the characteristics of the things that Fred Brooks talked about in his paper for the virtual reality applications that worked were the ones that involved things where you were in the midst of something big, piloting a ship, piloting an airplane. Those are all things where it's a big thing that you're in amongst, and that's important. Even learning about fear of flying, that's something where that fear is surrounding you in a way. I don't know if it's all visual, but it's not something that you would get from looking at a picture, a single picture. So that's a really good point. So that was one of our application areas. A second one was looking at microscopy data of biological systems. So this is 3D stacks of microscopes taken with a light microscope, and then volume rendered in the cave. Now, you might think that this is also an outside looking in kind of task, but in fact, these guys really got in amongst their data and kind of grew it and shrunk it, and they used scaling much more. They would do tasks like marking every cell. So you see each one of those green spots there is a cell, and they were trying to go in and count them, for example. We had an interface that would let them go in and leave little marks, so you can see the little marks where they're counting a particular kind of cell. And in order to do that, they really had to get in and do that. They had to get in and zoom in, and the thing tended to get around and fill up the space a lot more. And here, I guess you won't be surprised, but I think it's interesting that these guys did have better performance in the cave than on the desktop or the fish tank display, and they preferred the cave. So they were asked which one they would come back to use more often, and they chose to go after the cave. And the third scientific example I want to pull up is a group of planetary geologists who were looking at data from Mars. Now, this is not the cave. This is a tiled display, just a 3x3 display. But it was about 4 times the resolution of a monitor. And this is something where they came back every week, sat down in front of it as a group, and talked about their data and slid it around. They had really large images that they wanted to try and understand and make decisions about. So I kind of summarized this piece of the 3 scientific areas in a kind of a ambiguous way. That the cave is faster and slower in terms of performance than fish tank, and we don't quite know exactly what tasks. You have a hypothesis, and it might be right, but I don't think we have a big enough N yet to determine if that's quite true. I also think that there may be some things about caves as they stood in 1998 that will make that testing a little bit unfair. We also found, perhaps even less surprisingly, that folks preferred and didn't prefer the cave, mostly as a function of whether they were able to do their tasks or not in the cave. Okay, so this cave was not the ultimate visualization display. So let me talk about some of the reasons why it wasn't. And a lot of that comes down to matching those visual perceptual characteristics that I talked about after the Holodeck and some of the things that did a better job, but which are very hard to buy these days. So these are the numbers I showed you earlier in the left column, the characteristics of the visual system of the eye and the back of our brain that processes the stuff from the eye. And these are the characteristics of the cave. So that cave had much lower spatial resolution by a factor of 4 in each direction, so really a factor of 16 or so. Contrast levels were down in the 10 to maybe 100 range, so that order of magnitude, almost an order of magnitude less than what you can do with your eye, and that's because they started out so dark. We weren't able to get a projector that was bright enough to kind of meet the needs of our visual system. Same thing was true for color, and color was even worse. Instead of the same sort of 100 to 1,000 levels of color, we really only had 1 order of magnitude. So just our designers, our RISD folks, came in and just cringed at the weakness of color things that we could do in the cave, and they were really constrained by that. Now they're used to, working with ink, black ink. So they have kind of black and they have white, and this was constraining to them in the cave, so it was kind of sad. At least with black and white, you have a lot of contrast. So the other thing that I think is interesting to call out about our visual system and these displays is their field of view, so how much we can see. In this case, a person can see about 90 degrees plus or minus horizontally, and about 45 degrees plus or minus vertically. I'm sort of going to where my hands disappear from what I can see when I stare straight ahead. So that's what we can see completely, including all of our peripheral vision. We really only see a small central circle of that in any detail in our fovea. But I think this field of view is a big thing about in which the cave makes a big difference. So I'll put some other examples up in just a minute to give you some more context there. But so for our eye, this plus or minus 90, in the cave we had in 1998, plus or minus 135. So we could fill the horizontal field of view and give you sort of 45 degrees in each direction to turn your head before you started seeing out the back of the cave. Now, in front of us, we really only went up 45 degrees. So as soon as you looked up a little bit, you saw that top edge. And that kind of was one of those curtain things that broke the illusion that you were in. Now, looking down, the whole floor was projected. So modulo a bit of a shadow from the projector casting on you, you could bring your head pretty far down before your peripheral vision started seeing out the back, the end of the floor behind you. So that was actually not so bad in that direction. So I put all these perceptual things up to sort of give a sense of, once again, the ideal or the ultimate display, but also to talk a little bit about these findings in the context of how these limitations might have affected what we found and whether we might be able to do better with something that better matched perceptual limits. So compelling demos, hey, brighter, higher resolution, faster frame rate, more compelling? I think so. You know, hypothesis, but I think we'll be okay with finding that that's true. So costly development. Yep, I bet we're going to get more costly development if we make all those things bigger and faster and we have more computers and more displays. So it's just going to make things more complex, and I think that complexity is going to be real. So we found that the spatial relationships were valuable, and I think we'll find that that's still true. I don't think that's really going to change very much. So we found that virtual contexts don't help in that particular looking in potato task. My guess is, just like yours, we'd see the same thing if we did that experiment in a perfect ultimate display. But I think there are cases where the context is going to matter. And I don't know if it's just the looking in versus looking out. That's certainly an interesting thing to test, but I think there's more complexity going on there. And I'd be interested to kind of tease that out. So speed and accuracy on task performance on the particular tasks we did, I think, again, it's going to depend on the task, but I think that some of the speed and accuracy people found with their performance was a function of limitations of the display rather than limitations of the people or the sort of the kind of environment or the virtual reality context. I think that, in other words, I think that some of that may come from the lack of brightness or crispness or resolution. That may give you better performance in the cave and kind of handicaps the cave. So I would expect to see different results there. I would expect the preferences to match that performance, except for maybe the sitting down thing, which I thought was, we'll have to see. So we've designed and we're building a new cave now, and we haven't finished it yet, but this is roughly what we expect it to look like. So it's going to hit most of the perceptual limits that I've talked about. So there are going to be a lot of projectors. Each one of these guys is one projector. If you remember on our square walls, each square wall was one projector. We now will have about 70 projectors overall. Each one's going to be a 1080p, Blu-ray quality digital projector. So, and they'll be about 50 inches on the diagonal. So it'll be like having 70 50-inch TVs all playing off a Blu-ray player. Everything will be blended, so it's smooth. And the geometry of this thing is a hemi-cylinder. So this drawing is a little bit old. We now are going to have they're going to be, right here you can see one door that slides back in to close off the cylinder. We're actually going to end up having two that come in. So you end up with half a cylinder in the front and another half a cylinder in the back. One of the coolest things is the floor. You're going to be standing on 5 centimeters of acrylic, clear, back projected floor display, which will also be at your perceptual resolution. And then also to try and keep away those curtain issues, we're going to have a partial ceiling that blocks off that thing right over your head where you couldn't really look up without hitting an edge. This has been hard to try to build. We have had a lot of trouble finding the parts. In particular, these projectors. We just found what we needed 2 weeks ago, and we're very excited now to be able to move forward on making the actual thing. So altogether, this is going to get us to a Retina cave. So just like as with the iPhone 4, when you stand in the middle of this thing and you look at the display, each pixel will hit one receptor in your fovea. So you won't really be able to see the individual pixels. It will be at the resolution limit of your eye. It'll run at 60 hertz, 60 frames a second, and match your speed and brightness limits as well. So one of the things that I think is going to be particularly cool about this is that, so this is a paper that Tom DeFonte and a bunch of his co-authors wrote about the future of caves, or the future of the cave. And they've been building a bunch of devices that use LCD displays, which are wonderfully bright and crisp and sharp, but they all come with bezels right now. So he's been trying to work out ways to minimize the bezels, and maybe those will go away at some point, but I think they're always going to be flat. So one of the things that we'll be able to do with the cave I described is to have a display that has bezels and one that doesn't have bezels. So we can put in virtual bezels, if you like. We can make virtual facets that will help to essentially mimic any kind of display and find out whether that actually matters. Right now, they're exploring a lot of stuff under the assumption that it doesn't, but I kind of question that assumption. So just as a point of context, I can show you some of the stats on, this is the eye in the 1998 cave that I showed you a lot of examples of, and you can see the much better match between the proposed cave that we're building. We still can't do the 10 to the 10th dynamic range of your eye. But we do get 360 degrees around in the horizontal direction, and we go from 75 degrees all the way to 180 now in vertical field of view. And just to put that in context, I wanted to show you sort of an iPhone 4 is a Retina display, but it only goes sort of plus or minus 2 degrees one way and plus or minus 4 degrees the other. And 24-inch monitors only goes 15 and 12 degrees. Even the 30-inch monitors, the ones over in David Ebert's lab, they only go a few degrees past this. So there's still a lot more visual space that we can fill up with an ultimate display. So the one thing I didn't really touch on at all, except peripherally, was the expensive development and modeling. So I'd like to just talk about that for a last minute or two. We teach a class at Brown and at RISD. It's jointly listed. It's called Virtual Reality Design for Science. We teach mostly RISD, actually about half RISD students and half Brown students, how to design virtual reality applications for scientists to use in studying bat flight. I told you already how cool bat flight is. So the tool that they use to author things is something called cave painting. And cave painting lets you fill space up with these marks that then get left behind hanging in space to make an environment. So in the class, we teach the students how to do this. And within about 2 weeks, by the second week of the class, they're able to make environments that are incredibly rich by using their own sort of inputs and images and tricks that they've learned in Photoshop and other places to build something like this library. This library is an environment for looking at bat flight. Here you can see a view where you're on top of this sort of, I don't know what to call it. It's like a big table that's the vision of this artist of where you would look at how the flow is circulating underneath the wing of a bat. And he built in an incredible amount of detail to this. You can, when you fly through this using the cave, inside the cave, you can really get a sense for just how complex this environment was. And he built this as someone who knows how to program not at all. So I think this is a promising direction in terms of being able to give folks some tools for creating interesting looking stuff without having to spend 2 years doing it. This is another example of an environment that one of the students built in the class. And I think it's just really a tribute to their creativity and sometimes to their persistence in using this environment with the kind of richness that they're able to create in this. I'll also say that we're putting out 3 libraries of open source software that will help to make cave development easier and less costly as well. One for doing the 70 display kind of thing, one for blending projectors, and what was the third one? Oh yes, and another for monitoring all the things that need to run to keep the cave up and going. So thank you, and I hope I've given you a little bit of a flavor of what an ultimate visualization display might look like today or in 300 years maybe. And I welcome any questions. Yeah.
What are your difference between the brain scientists and the microbiologists? I wonder if training with the brain scientists, you have people who are trained to think at a human scale.
Could be.
As opposed to people who are used to dealing with a non-human scale and having to vary the scale continuously.
Yep.
And whether that makes it easier for them.
That could be. And if we threw the brain guys in with a brain that was 6 feet tall, they might have done something different too. So I don't know the answer. It's a good question. We'll try it in the new cave. Yeah.
So the display that you're building, you're trying to address some of the limitations that you have identified in the older generation. So one that seems to remain is the discontinuity that's introduced between the walls and the floor and ceiling, unless you have some specific way to prevent that.
No, so you're right. We did notice that corners were a problem, particularly the wall corners.
So you seem to have eliminated those?
We have eliminated those almost entirely. There are two 135-degree corners where the back door comes together, and there's a place where we won't blend across because you have to have the door has to have something to hold it up. But we couldn't figure out how to make a wall that was completely transparent, curved at the top and the bottom, and curved all the way around, period. So.
What about these further displays that they have in astronomical?
Those are all projected from the outside, aren't they? I mean, from the inside?
No, not all of them.
No?
Like in New Mexico, they have some that are from the outside.
Okay, I don't know how to, I hadn't seen that, but something like that might be possible.
Yeah, they build a dome and...
Right.
In fact, I'm quite sure it's from the outside.
Yeah, I would look at that. I think that most of those are geodesic kind of construction where they're often faceted, at least they're small facets, and they tend to be triangles, which are harder to use square, rectangular projectors on. So we talked about also making a kind of a toroidal section somehow that would blend across that ceiling. But in the end, we decided we couldn't do everything. We would have liked to. And at some point, if we get $1 million from somebody who thinks that that corner is important, we'll see if we can fix it. Do you have your checkbook?
How stiff is the mechanical engineering?
How what?
How stiff is the mechanical engineering? Keeping the thing from vibrating?
I don't know about vibration. It's been...
With the air,
It's been, yeah, it will move around some. But the projectors have very, very deep field of, what's it called? Yeah, they're long throw, but they also have a depth of field that's significant. So it should stay in focus. It may, we may get little bits of wiggle with some of that. It's 2 millimeter acrylic, bent. So it should be, it shouldn't be too bad, we hope.
So it's rigid?
It's, well,
it's not...
it's not rigid like aluminum.
Right, but it's not just a cloth.
It's not cloth. It's like a piece of plexiglass. So it's a 2 millimeter thick piece of plexiglass. But when you get that 8 feet tall, it definitely has some, some wiggle room. Yeah.
Do you find that people want to walk inside the cave, or do they tend to love the ability to fly?
Oh, walk or fly. I find most people that go in the cave sit or stand still. And only when you sort of prompt them and say, you could walk around, do they say, oh, okay. I think that, there's only so far you can walk. It's not a giant space. So really you're not walking, you're stepping and looking here and here.
Cheat a little bit to multiply.
Yeah, you could do a little bit of that, but if you need to move any distance, you have to fly. So people have put treadmills in to try and do that. Yeah. So, and ones with force feedback. They had one at Utah that they had a kill switch on that was kind of scary to get strapped into.
With a tether or some sort.
Yeah, yeah. You could see the thing picking you up and slamming you against the treadmill. That thing tilted and pushed you and made you feel like you were climbing uphill. It was interesting.
So how will you add haptics to the display? Because that was your first slide, so now you have to.
I'll just buy a holodeck.
A holodeck?
I don't have a good answer to that. I think it's just too hard right now. I think the richness you need in haptics is way beyond what is even people are even thinking about today. So we have a huge number of, touch sensors all over, and it's just we have no way to stimulate those right now. Do you have any ideas?
It has to be a bodysuit of some sort, right? It has to be close to the user.
How about like some kind of, brain stimulator? What's that?
Or you need the projectors.
Yeah, maybe not. Maybe you don't need the projector then either. I don't know.
I mean, the output display is very much fooling the eye, right?
Yeah. Well, and the whole visual system, which is half the brain too. Well, I think we're beyond our 3:30, so we should maybe.
Okay, so that's where they are.
Okay.